Thank you all for coming. Welcome to lecture 5 of our course. I hope you're enjoying the course so far. Last lecture I wanted to do, but I couldn't because I had a flu and I couldn't really speak. This week it's much better. I think Tanush did a very good job doing the last lecture. This lecture today will be on computer vision. The lecture itself will be a bit more dry because we have a bit less quizzes, a bit less programming or live programming, but we need to go through some of the basic elements. And then afterwards we have the tutorial where you are able to put all these elements together and actually program yourself. Those as well. I didn't put them on a slide before because you know the concept of activation functions already. So we'll just put it into neural networks later on. Okay, let's look at the actual neural network. So basically, what we have is in a neural in a convolutional neural network, we usually have 3 steps: convolution, nonlinearity, and pooling. And what we do is we usually have them in this order, and we usually repeat them multiple times. So you can think a bit about this one as one layer in a neural network, but now we have this in a convolutional neural network, right? And more specifically, we say this is a pooling layer. This is a nonlinearity we don't call. This is a pooling layer. This is a convolutional layer. Nonlinearity we basically include in the convolutional layer, usually. And in the convolutional layer, we apply the filters. So what we put here is we put 3 exemplary filters. In this case, we start with a 2D image, so we don't have a colorful image, just for simplification, but could be colorful image in general as well. If we have a colorful image in the beginning, we would have these 3 matrices, right? And then the filters would have 3 matrices as well, or tensor. So by applying 3 different filters, what we get is basically 3 different channels here as well. And I'm not sure if you recognize, but this filter here and that filter here we had before already, right? So they basically extract here the vertical components of the image, here the horizontal ones, and this one here, I'm not sure what it does actually. The diagonal ones. Okay. So if you look here, you see, these ones are eliminated. Love it. So Max is working a lot of computer vision, much better than I am actually. I'm not sure why he's not doing the lecture. But if you look carefully now, you see that here are, and maybe you see it on a PDF better, like lines that are in a 45-degree angle, right? And here those are removed. So this is what this filter is doing. And again, these are, in this example, just predefined filter. Later on, each of these values here will be parameter of our model, right? So we will train those. Then we add the nonlinearity, and that's usually just a ReLU activation function that we apply. And then we do the pooling in order to reduce the dimensionality again. So the result of this configuration here are essentially 3 channels, right? 1, 2, 3. So what we can do is we can now take all of these together, consider that the result of our first layer of the neural network, and then we can reapply that, and we can add the next one here. We repeat that n times, and in the end we have these feature maps, right? So we have a number of images, kind of. It's not real images because it's a result of these feature maps. We can still look at it as it would be, a grayscale image or a number of grayscale images. But the key problem is still, how can we get from these feature maps to one prediction, right? So we wanted to have this vector at some point that tells us, is that now a car or an image or a PNID or a PFD or a reactor or distillation column or whatever. So how can we do this trick? And that's something like a very common problem we have in machine learning. And there's a very simple answer to that. which is we flatten the image. So basically what people do is they just take, this here as the first vector, and then the second line they just add to the vector, so they concatenate it, so they just get a very long vector. And if we have a very long vector, well, with vectors we worked in the first lecture already, right? So vector we can put into a neural network, and we can do the standard classification problem. And that's what we do here as well. So at some point we say, hey, that's it. That's our last feature map. Now we just concatenate, or we flatten our image. So we make it a very long vector, and we put that to a normal neural network, and the normal neural network will just make the prediction, like in lecture 1 and tutorial 1. Okay? But these are not two separate steps. So it's not like we first do all of this one here. I give you the vectors for each image and you give me the prediction. No, we want to train all of this together, right? So it's an end-to-end learning approach. So the image comes in here, the prediction goes out there, and that's where we calculate our error, and that error we use in order to update all the parameters in the normal neural network. But at the same time, we also update all the filters and parameters in this part here. So basically, the problem is more complex because we have images, so the model becomes a bit more complex. Is that clear from a bit more conceptual point of view? Yeah? And then one more thing is this one here is usually called some kind of embedding vector. So basically what we say is we try to go from the image to this embedding space. And the idea is, the concept is, ideally, now we created a space where two cars are actually two similar vectors. Right? So that was a key issue. If we have two car images in the beginning, if we look at the matrix values, they don't look similar. Or if we have two different angles taken from the same scene, the vectors are, the values of the matrices are not similar. The goal is that if we create these vectors here, they will be similar. So here, two cars should, the vectors, the distance between the two vectors of two different images of two different cars should be very similar, because if they are similar, then the neural network approach here works. And the magic is that through training, it actually works. Because of course it looks strange, right? So this vector might have hundreds of dimensions. And I think we come to that in the last lecture when we talk a bit about natural language and so on. And there we do a very similar approach. We start with something strange like sentences, and the real goal is to map those to a vector space, to an embedding space, because once we have that, we can use all the standard stuff. We can use standard neural networks and everything works like a charm. Okay. I think what we have now is we have a real model. So a real successful machine learning model. Just to give you an idea of how complex that stuff is, how many parameters we're actually looking at, and what deep means, right? So we talked about that in the beginning as well. When we talked about standard neural networks, and we said something like deep is if we have 2, 3, 4 layers, whatever. But then now the problems are more difficult, so we need to stack more layers. And this one is one standard architecture that is very commonly used and very successful for image classification. It's called VGG16, and there's a meaning for that, Visual Geometry Group. I guess that's the group that developed that model. And then 16 means this one has 16 layers, essentially. And if you look at how people illustrate these machine learning architectures in computer vision, usually they have these kind of images. Sometimes there's one other way to represent it where they, each of these filters looks the same, but then they put the size in the description box. So if you search for VGG16, most likely you will find this image or another way of representing this. And then always you have these descriptions here, and you've seen those already, right? So this one is the dimensionality, this one is the number of filters. And we will now go through a few of these layers to explain a bit what is actually happening, and to show you a bit that actually you already understand all of these elements. We just really need to put them together